Remember when we talked about r squared and I told you it was a very widely used measure of explanatory power? Well, that was almost true. We'll have to refine this measure. Its new version will be called the adjusted r squared. A statistician would always take a look at it when performing regression analysis. So, what does it adjust for? Let's consider two statements we saw in the previous lessons. 1. The r squared measures how much of the total variability is explained by our model. And 2. Multiple regressions are always better than simple ones. As with each additional variable that you add, the explanatory power may only increase or stay the same, considering the number of variables. The adjusted r squared is always smaller than the r squared, as it penalizes excessive use of variables. Let's create our first multiple regression to explain this point. I'll import all the relevant libraries once again. This time, though, I'll load the data from the file 1.02 multiple linear regression.csv. That's the file relevant for this lecture, and you can download it from the course resources. As you can see, we have the same data with one additional variable called random123. I've generated a variable that assigns 1, 2, or 3 randomly to each student. We are 100% sure that this variable cannot predict college GPA. So, this is our new model. College GPA is equal to B0 plus B1 times SAT score plus B2 times the random variable. Here are the descriptive statistics. What about the regression? Y is still GPA. This time, though, we have two explanatory variables, SAT and random123. What we can do is declare x1 as a data frame containing both series. Great! The rest remains unchanged. Let's run the code and check out the newly created regression tables. You can see the old ones in the box on the right. We notice that the new r squared is 0.407, so it seems as we have increased the explanatory power of the model. But then our enthusiasm is dampened by the adjusted r squared of 0.392. We were penalized for adding an additional variable that had no strong explanatory power. We have added information but have lost value. Point is, you should cherry-pick your data as to exclude useless information. However, one would assume regression analysis is smarter than that, right? Adding an impractical variable should be pointed out by the model in some way. Well, that's true. Look at the coefficients table. We have determined a coefficient for the random123 variable, but its p-value is 0.762. Remember the null hypothesis of the test? Beta 2 equals 0. We cannot reject the null hypothesis at the 76% significance level. This is an incredibly high p-value. Let me remind you that for a coefficient to be statistically significant, we want a p-value of less than 0.05. Our conclusion is that the variable random123 not only worsens the explanatory power of the model, reflected by a lower adjusted r squared, but is also insignificant. Therefore, it should be dropped altogether. Dropping useless variables is important. You can see the original model changed from y hat equals 0.275 plus 0.0017 times x1 to y hat equals 0.296 plus 0.0017 times x1 minus 0.0083 times x2. The choice of third variable affected the intercept. Whenever you have one variable that is ruining the model, you should not use this model altogether, because the bias of this variable is reflected into the coefficients of the other variables. The correct approach is to remove it from the regression and run a new one, omitting the problematic predictor. There is one more consideration concerning the removal of variables from a model. We can add 100 different variables to a model and probably the predictive power of the model will be outstanding. However, This strategy makes regression analysis futile. You are trying to use a few of independent variables that approximately predict the result. The trade-off is complex, but simplicity is better rewarded than higher explanatory power. Finally, the adjusted R-squared is the basis for comparing regression models. Once again, it only makes sense to compare two models considering the same dependent variable and using the same dataset. If we compare two models that are about two different dependent variables, we will be making an apples to oranges comparison. If we use different datasets, it is an apples to dinosaurs problem. As you can see, adjusted R-squared is a step in the right direction, but should not be the only measure trusted. Caution is advised, whereas thorough logic and diligence are mandatory. In our next lesson, we will learn how to assess the overall significance of a model. Thanks for watching.